Okay, so this is another video lecture for Math 1053 at UTSA. This is Module 2. Again, I didn't make the original PDFs here, so I don't know why Module 2 isn't just in the file, but whatever. Anyway, so Module 2 is all about functions, and I'll skip talking about what a function is by definition, because presumably you've done the guided notes or the textbook notes, whatever we call them this time. Presumably you've done those and you know more or less what a function is. Let's focus on how to answer these problems or these questions. So which is a function, which is not. So these are all different representations of potential functions. So you can have like these ordered pair lists, and basically like this is an input, this is an output. So this is like saying that f of a equals b. It's an input-output pair. Okay, kind of like here, this is an input variable, this is an output variable. So if there's a function here, then f of something equals something else, but I'm not given like a list of objects. And then here we have a graph, so that like a given point has an x coordinate and a y coordinate, which would be input output. So these are all different ways to represent the relationship between a set of inputs and a set of outputs. Sometimes you just want a list, sometimes you need an equation, sometimes you want a graph. There's just different ways to do it. So the main thing, what distinguishes a one of these things, which the general term is a relation. So these are all definitely relations. A relation is any mathematical thing that relates to a set of outputs to a set of inputs, and vice versa. So these are all relations for sure, but a function is one in which you can't have one input resulting in multiple different outputs, right? So here we've got A as an input makes B as an output, but also A as an input makes C as an output. That's not allowed. You can't have the same input resulting in two different outputs. That makes it not a function. It is a relation, but it's not a function. So this one is not a function. Okay. Over here, this one's kind of similar in that we do see something repeated, like, oh, this output C is repeated. So there's more than one input that produces the output C. Is that not allowed? Well, that's actually fine. The outputs can be repeated. It's the inputs that can't be repeated. Like over here, we have A appear as an input twice with different outputs. That's not allowed. Over here, we have C appearing twice with different inputs, but that's okay. It's okay in a function for, for two inputs to result in the same output. That's allowed. Why is that? Well, that'll become more clear in a minute. Okay, so this one appears to be okay. Basically, what you want to look for is is the input variable ever repeated, or input value, I should say. And if so, is it just redundant? Like if you took this list and just sort of tacked onto it, said, well, actually, no, it doesn't end there. We also have like A, comma, B as like another ordered pair, right? Well, that means that we're repeating this ordered pair AB twice, which is just redundant. That doesn't disqualify this new list from being a function. It just means we have a redundancy. So ignoring redundancies, you basically look for, does an input value ever get listed twice? And then if so, ignoring redundancies, well, then that's a problem, right? If it happens, there's merely redundancy, that's okay. But look at our inputs, A, B, and C. We don't have a repeated input. And since the input is not, the input A is not listed twice anywhere, the input B is not listed twice anywhere, input C is not listed twice anywhere, this is a function, okay? Now, again, it would be okay if the input is listed twice and it's just a redundant term. Like if we had B, comma, C listed twice, that would be fine. It'd just be a little bit weird because why is it redundant? So this one is a function. We'll just say is, okay? All right, so that's how you handle it when you just have these ordered pairs. And again, the why might not be so clear. Why is it that you can have the output repeated and given multiple times, but the input can't be used multiple times? Like, why is it like that, right? So we'll get there in a minute. So looking at this one, we're asked if this represents a function. Now, this isn't a list of ordered pairs, like an input-output pair. Excuse me. But if you pick an input, like say you pick x equals, say 5, just to pick a number, right? Then is it possible to have multiple different outputs resulting from that input of 5? And the answer is no. If you plug in 5, just as an example, right, you'll have 3 times 5 squared plus y equals 14. Subtract 75 on both sides. So y equals negative 61, I guess. Even if my arithmetic is off, you get something, right? You get a calculator if you need to. You'll get something, right? Y equals one number. There's no way to get two results. No matter what I pick, you can, whatever I pick for x, which remember x is the standard input variable, whatever I pick for x, I will always be able to get just one number for y. One way to see that, and maybe it's obvious here because the arithmetic would be the same, right? You plug in a number, square it, times 3, subtract to the other side, and you would get some number, right? Another way to see that is if you can isolate the variable y, which is the standard output variable, then it's maybe more clear. So if I just subtract 3x on both sides, so I have y equals 14 minus 3x squared. Subtracting 3x squared on both sides, right? Not 3x. I misspoke. So if I can get y by itself, and then this is just a formula with x, then whenever I pick a number for x, I'll get a single output value for y. I will always just get the 1. So this one is a function. Okay. Now I'm going to guess that the other one is not. I haven't looked at it yet. Okay, yeah. So this one's not a function. Now, to me, it's obvious because I'll tell you why it's obvious to me. Like, what's the clue? And then we'll look at confirming that actually it's not a function. So if you've got an even exponent on y, that means if you pick a number for y, remember y is the output variable, not the input variable by default. Y can be an input variable if you want it to be, but by default, we assume it's not. That's just standard. So, well, let's just do an example. Let's say you pick a number for x. Let's say I pick 1. X equals 1. Okay? Maybe that will be the easiest way to illustrate this. So x equals 1. So I'll plug in 1. So 2 times 1 plus y squared equals 6. I'll subtract 2 on both sides. Y squared equals 4. Now we could ask, okay, well, what is y, right? It might be very clear to you. Well, these numbers aren't like difficult numbers. Like y is 2. But y could be negative 2, right? Y is equal to plus or minus 2. Okay. There's a couple ways to think about why that is. And if this were like a live lecture in person, with me and like 50 people or whatever, listening, someone might suggest something at this point. Now, there's no one here to do that. So if you're like shouting at your screen, hey, aren't you supposed to do this? That is something where you might want to send me an email to ask, hey, is it this? Or ask for, like, it's next time you talk to me about during office hours for whatever it may be, you could bring this up and say, hey, was it this? So there's something that you might suggest, and I don't want to, put words in your mouth/ears. So I'll just leave that out unless people ask about it. So the point is, though, that if you pick a number for x, sometimes you're going to get two possible outcomes for y. And that's because y is squared that happens. So when I see y squared, that's my clue. Oh, this probably is not a function, okay? And then when I check numerically with a specific example, I find out that, yeah, for the x input 1, there are two possible y results. That's not a function, okay? Now, why do we care about that? Well, there's a couple of reasons. Maybe the most straightforward reason is, which we'll see more clearly in the graph here, is it's not that you can't do math with relations. We have a name for them, and you can do math with what's called a relation instead of a function. But when you go to do calculus, which is the class that comes after this one, right? Next semester, you're taking calculus, right? When you do calculus, you kind of have to start by doing calculus with functions and not relations, because with relations, it's more complicated. You have to figure out how to deal with calculus in a function before you can deal with calculus on a relation, because it's a little bit more difficult, a little bit harder. Okay, so basically, we want to identify, we want to distinguish functions from non-functions, because there's certain things that functions do that are just easier, and we want to stick with the easier thing whenever we can. Doing algebra and calculus with relations that aren't functions is more difficult, so we want to kind of get hung up on that. So we focus on functions because it's a little bit easier. That's one of the reasons. Anyway, so looking at this graph, okay, I can look at this and I can tell that there are 2 points right here at 2, 0 and at 2, 2, okay? So this is one of the reasons we think about the functions in terms of ordered pairs, because when you have a graph, you can also identify ordered pairs. Notice how we have the input 2 repeated with 2 different outputs. This is not a function because the input 2 results in 2 different possible outputs, kind of like this one did, right? The input 1 resulted in 2 different outputs, 2 and -2. So really, the graph of this equation is actually very much like this one. It's not the same, but it's very similar, the way the graph looks. A way to summarize what we're doing here is called the vertical line test. If you make a vertical line, let's make that a thicker vertical line. If you make a vertical line on a graph of some function, and you look for, does the graph cross twice? Because if it does, well, does the line rather cross the graph twice, or vice versa? Because if it does, that's an indicator. Oh, here you have an input with 2 outputs. That's not a function. Okay, basically, the reason for that is to summarize what I've kind of been saying already is if I say I have f of 5, that should equal a single value, a single output. So I don't have to like choose, right? Because if you're dealing with this thing, you go, oh, well, what's f of 2? Well, do you want the top half or the bottom half? It complicates things because then every time you try to go do something with the formula, the function or whatever, if you don't distinguish from relations, well, then you're going to have to choose top half, bottom half, or there might be 3 choices, right? If you have a graph that's more complicated than this, there could be 3 outputs for the input. And then now every time you want to do something, you have to decide which output to use, right? That's a pain. That's a hassle. It's a complication. So we don't want that. So we'll say that, oh, we're not going to do algebra and calculus with this kind of, this kind of graph because it's a hassle. We're going to stick with things that are more like this one. Okay, which the graph is very similar. Like obviously, like this is kind of the same shape. It's just rotated. But with this one, if I pick a vertical line, just basically anywhere, if I go say here, right, and I say, oh well, does this cross more than once? And it does not. This crosses exactly 1 time. And no matter where I put a different vertical line, it will only ever touch the graph at 1 place, and that tells me that when I plug in an input value, excuse me, I'm getting a single output value. So f of 5 is something. In this case, f of 5 is not on there because 5 would be like way over here, right? So it's not on the scale. But like f of -2, that's -3, right? This ordered pair right here is -2, -3. So I know that f of -2 is -3. And I don't have to decide top half, bottom half, or anything more complicated than that. Okay, that's basically why we want to distinguish functions from relations. So yeah, there's that. Just sort of conceptually, how do you identify a function, right? Okay, so now we're going to do some more stuff with functions. So determine the following for the function g of x equals x over 12 minus 3 over 16. Okay, so first we're going to plug in some numbers. First we'll plug in -9. So this equals -9 over 12 minus 3 over 16. Now, I could say that's my answer, but let's combine like terms. Let's simplify this a little bit. I noticed that in this fraction, the top and bottom are both divisible by 3, right? They're both multiples of 3. So I'll reduce this to -3 over 4 minus 3 over 16. Okay. And also now, I kind of want common denominator, right? So I can actually combine these. So that left fraction, rather, I almost said inequality, left fraction, -3 over 4, that needs to be scaled up to have the proper denominator. So I need to multiply the top and bottom of this one by 4 so that I'll have 16 on bottom. Okay. So I'll have a -12 over 16 minus 3 over 16 equals -15 over 16. And I would strongly encourage you, when you're doing the homework, only use a calculator. Let's put it this way. So looking forward, not next week or next month, but next year or next semester, rather, possibly next year. If you rely on the calculator to do all of your arithmetic for you, then your arithmetic skills will not get better. You might like become a little bit rusty on arithmetic over time, like over a long time, right? But your arithmetic skills won't get better if you're relying on the calculator all the time. Why am I bringing this up? Why is this important? Well, all the rules for algebra are layered on top of the rules for arithmetic. And if you're really solid on the rules for the arithmetic, you can do like basic arithmetic on paper with a pencil, no problem, right? That would be great, because then when you need to leverage those skills to do algebra, it will be a little bit easier, right? And then later, as we develop our algebra skills, and as you move into the next class, the calculus class, calculus is layered on top of algebra, right? So you can leverage your algebra skills that you've developed and honed in this class to do calculus in the next class. So if your arithmetic skills don't get stronger over time, then your algebra skills are kind of capped out at a certain level, because they're layered on top of those arithmetic skills, right? And I want you to have the easiest time possible in the calculus class. Like, it's gonna, even like if you get an A+ in this class, then you're gonna have a little bit easier time in calculus because you become more solid in the foundational stuff, right? Anyway, all this to say, when you're doing the homework, do some of the arithmetic by hand, even stuff that you know how to do. But the calculator will do it like a lot faster. You're like, oh, I know how to do this. I just want to get the homework done faster, which I understand that motivation, of course. But if you want to squeeze every last drop of benefit out of doing the homework, do some of the arithmetic by hand from time to time. Not all the time. And on a timed quiz or a test, yes, calculator, of course, when it's timed, right? But when you're just doing the homework, spend a little time doing the tedious stuff as well. The stuff that's relatively easy, but it's tedious. That's gonna benefit you over the long term and make the calculus class a little bit easier for you when you get to it. And anyway, I'll get off my soapbox now. So, so we get -15/16, right? So now we're going to do this one, which is very similar, but the negative, instead of being inside with the 9, it's outside. Okay, and that might seem like a really minor thing, and I guess it's minor, and it's a very small change, but it has an effect on the result. You won't get the same result. Yeah, so if you take, excuse me, a minus that's inside and just move it outside, for most functions, the result will be not the same. You'll get a different result that way. There's a classification of functions called odd functions, for which when you do that, the result doesn't change. Those are called odd functions, but most functions are not odd functions. Like 98% are not. I made up that number, of course. Anyway, so I want negative g of 9. So this is going to be negative of g of 9, which is, you plug 9 into the original function, 9/12 minus 3/16. And I want you to notice is this minus here, this applies to this whole group, not just the 9/12, which is how it differs from here. Because up here, excuse me, hold on a second. Sorry, I had to clear my throat there. Anyway, so up here, the minus applied just to the numerator of the fraction 9/12, because the minus was with the 9. Now that the minus is outside, the minus applies to the entire group, and it therefore is going to make this -3/16 into a +3/16. So we get a different result that way. Okay, so that'll be, and the arithmetic will be basically the same. So we have negative, and I'll keep the parentheses for now. So that 9/12 become 3/4 minus 3/16, which I guess I'll go ahead and distribute. This is -3/4 plus 3/16. And then again, this fraction here needs to be scaled up to have the right denominator. So I'm going to multiply top and bottom by 4. So I'll have -12/16 plus 3/16. And we get -9/16 as a result. Okay. So clearly not the same answer, right? It's different because that minus, the positioning of that minus sign makes a difference. So last one, this one wants us to solve the equation g of x equals 9, which might look a little bit weird. You might not be sure what that means. All that's saying is that we're going to take this g of x formula and plug it in down here and have that formula equals 9, and we're going to solve that equation. Which, how much vertical space do we have? Not a whole lot. Okay, so I guess I'll put that up here then. So this will be x/12 minus 3/16 equals 9. Now there's a couple of ways to do this. I find that I prefer, what I think is easiest. When I have fractions in an equation like this, fractions can be a bit of a hassle, as we've noticed, right? So what I'm going to do is I'm going to figure out what is the least common multiple of 12 and 16, and then we'll multiply that on both sides of the equation, and that will get rid of the denominators. So we will have no fractions, at least temporarily, although our final result probably will be a fraction. So 12 and 16, you might not be, you might not recall, or maybe you do, how to find the least common multiple of two numbers. And sometimes it's real straightforward, sometimes not so much. One way to do this is to think about the prime factorization of these numbers. So 12, this factors, and I'll assume that you know how to factor a number to its prime factors, and there's more than one way to do that. So I'll just assume you kind of already have a way. If this is something that you need more detail on, definitely send me an email, we'll get on a Zoom call, I'll help you figure it out. You could also just YouTube least common multiple of two numbers. That would probably help as well. Anyway, so this is going to be 2 squared times 3, right? Because 4 times 3 is 12, and 4 is 2 squared. So that's the prime factorization. This one, this is 2 to the 4th power, okay? Because 2 times 2 is 4, times 2 again is 8, times 2 again is 16. So the least common multiple of two numbers, it needs to have all the same prime numbers that either one has. So our least common multiple is going to have both 2 and 3. Okay, those are only prime numbers involved. And the least common multiple, I guess one way to say it is you take the number of copies of 2 that we'll use is the greater of whatever we see on the screen. So we've got a 2 squared, and we've got a 2 to the 4th. You take the bigger one. 2 to the 4th will be the number of how many 2s you need to be in that least common multiple. And then you look at the next prime, which for us is just 3. There's only one 3, so we need 1 copy of 3. So the least common multiple, that is going to be 2 to the 4th times 3. We're taking, excuse me, as many 2s as the greater of the 2. We don't take 6 copies of 2. It's basically these copies of 2 are redundant and not needed because we have more over here. And you take whichever is more, and that's how many you actually use for the multiple. Okay, and maybe that's obvious, but maybe not. So I just wanted to point that out. Whichever has more of them, that's the ones you keep. So if you multiply this out, you get 48. Okay, so I'm gonna multiply 48 on both sides up here. And particularly on the left, you could think of this as being, let's get rid of that. You could think of, on the left, think of this as being 48 over 1 might be helpful for multiplying the fractions. So when I do that, when I multiply this fraction against this one, I'll multiply the 48 with the x and the 1 with the 12, right? And since I'm distributing, this one also goes over here, and I multiply 48 with 3, and then 1 with 16, okay? Now what I'm going to do is I'm actually going to write out 48 times x and 1 times 12, so we don't lose track of how we got these pieces. And then 48 times 3. And there's actually 2 reasons I'm doing this. You'll see in a minute. And on the right, 9 times 48. I guess that's a 438, 32, 432. Calculator time. I'm pretty sure that's right, but I've been wrong before. Yeah, 432. Awesome. Okay. So, focusing on this left-hand side. Let's look at this one first. This one is the reason I didn't total up the products. Like I wrote 1 times 12 instead of just 12, 1 times 16 instead of just 16, and then 48 times 3 instead of what is that? 146, I guess. 144. Okay. So instead of having to do the work, case in point, instead of having to do the work of coming out with 144 is this product, I'm going to reduce the 48 and the 16 to be 3 and 1. Okay? So I never have to do 48 times 3. I just don't need to do that product. I never need to. I can avoid it by canceling, by reducing before multiplying. So kind of like, this is one of the things I don't like about PEMDAS. And I alluded to this in the other video, so let's talk about it a little bit more now. So PEMDAS. Okay. This is sort of misleading because it kind of makes it look like, it kind of implies that multiplication goes before division, but it simply does not. In PEMDAS, and remember I've said before, PEMDAS is a recipe that always works. It's not the only way to do things. It's just the easiest to follow, I guess. It's PEMDAS. It has a mnemonic, right? You follow the mnemonic. You just have to learn not to get misled by it because it's a little bit misleading. M going before D, multiplication before division. So what I've noticed when people are doing fractions like this, they really want to do multiplication before division, before 48 divided by 16. I think PEMDAS is part of the culprit there because it gets so used to thinking, oh, multiplication goes before division, but it simply does not. They go at the same time, and one way to do that is to go left to right, top to bottom. That works. I prefer to go top to bottom first. So instead of saying, oh, I'm going to multiply. Oh, I'm hitting undo and undoing all of that now. All of that over there. Hold on. I want that to stay. Yeah, okay, cool. So instead of doing like 48 times 3, I do 48 divided by 16 first, because if I don't want to use a calculator, then dividing first makes a lot of sense. So like over here, right? 48 divided by 12, right? So 4 and 12 reduces 4 and 1. So now on the left, I've got 4x minus 9 equals 432, okay? And although my answer will be a fraction, I don't really have to deal with fractions that much until the very end. So I'm going to add 9 on both sides. So 4x equals 441, and then divide by 4 on both sides. So 441 over 4. So this problem could be done differently. What you could do instead of multiplying by 48 on both sides first, you could get a common denominator of, well, I guess it would be 48, right? And you could get a common denominator and combine the two fractions into one fraction and go from there. That'll work. I find this to be a little bit easier. To me, this seems easier, but that's subjective. So if you learned a slightly different way to do this, or you find a different way in the textbook or on YouTube, that's absolutely fine. However you think is easiest is how you should be doing it. Anyway, let's move along from there. So the next part is a little bit complicated, but it's really important for this class and because you need it in the calculus class. And if you learn this well here, then when you get to the calculus class, the beginning will be relatively easy for you if you're pretty solid on the algebra involved here. As I mentioned earlier, calculus is layered on top of your algebra skills, and the stronger your algebra skills are, the easier calculus will be for you. And just like algebra skills are layered on top of arithmetic skills, and the stronger your arithmetic skills are, the easier algebra is for you. And as you go through this class, try to develop both arithmetic and algebra, so when you get to calculus, it'll be as easy as it can be for you. It's still calculus, it's still work, but you can prepare for it, basically. Anyway, so kind of like how we were plugging in 9, or negative 9 rather, you can also plug in a whole expression with like variables and stuff. So here, we're going to plug a plus h into this function for x. So it's going to replace the x in x squared. And we're going to have parentheses. So we're going to have parentheses around a plus h, and then that group is squared. So this will be a plus h. Oh, not a plus 2, sorry. A plus h squared. I was thinking about 2 while I was trying to write h. Minus 16. And then, like, if you were to put this into WebWork, it might take it just like that. But we're going to need to simplify this in the future for like, this part especially. So I'm going to write this as a plus h times a plus h, all that minus 16. And I'm going to guess that y'all know FOIL already. So I'm not going to go into great detail about why FOIL works, but we'll walk through the process. So FOIL, as you probably know, is first, outer, inner, last. First, outer, inner, and last. Okay. I have a feeling that the video I made last week also covered this, but we'll cover it in detail again anyway. But in the future, I might gloss over foiling from time to time. So first, that means in each parenthetical chunk, you take the first thing that appears, so a in both cases, and you're going to multiply those together. So a times a is a squared. Okay. Then you're going to go to the outer, whatever is the outer pieces. So thinking about the parentheses being the center, you want to take the two outer things, a and the h in the second factor. So a times h. Okay. Okay, plus the inner. That will be the two things closest to the center, h times a. Now, h times a, this is the same as a, the same as a times h, right? If you think about 2 times 3 is 6 and 3 times 2 is 6, when you're multiplying two things together, the order doesn't matter. If you were to go learn more algebra, including matrices, which this course doesn't cover, there are exceptions to that. But for numbers, when you're multiplying, the order doesn't matter. Likewise, variables like x, y, z, t, a, h, all these letters, when you're multiplying two together, the order doesn't matter. So AH and HA are really the same thing. So I'm going to write this as plus AH. And the only reason I'm doing that is it'll make it more obvious how to combine like terms in a few minutes or a few seconds. Okay, and then last. The last means in each group, each parenthetical chunk, take the last thing, multiply those two together. So h times h makes h squared. If you find that this is a little bit hard to follow, there's a technique called the box method, which I'll show here in a second, that you can use. But we'll get to that in a second. So I now have some like terms. I have two terms with the same variables present. These two are different because not both of them have an h and not both have a squared copy of a. And these two are not the same because they don't both have an a at all, and they don't both have a squared copy of h. Whereas these two are exactly the same. They're each one copy of a times h, so we're going to have 2ah as a result. So a squared plus 2ah plus h squared minus 16, okay? So that's that first part, 7. Now, you might wonder what a is and what h is. That is something that is really a calculus thing. So we're doing this here so that you can develop the algebraic skill of the difference quotient, and what it represents is something that we'll talk more about in the calculus class. Probably in the textbook it mentions it, but I think we should just not worry about what it is. If you're really, really curious about what it is, email me, Zoom call, we'll figure it out. I'll show you what it is. If you really want to see, I don't mind showing you, just I don't need to make everyone watch a 5 to 10 minute explanation of what it is when you don't need it to do the homework, right? Next semester, we'll be using this to do something, and at that point, that'll be made clearer. Again, you could just ask if you want to. So what did I mean about what's called the box method? So let's go over here off to the side. If I have, I'm going to pick, yeah, I'll do the same thing. That's fine. So if I have a times, or rather a plus h times a plus h, maybe I'll do it with a different group as well. I can do what's called the box method by doing this. And I don't normally do this, so I might stumble a bit, but I think I remember how to do it. So basically, you have this sort of grid, right? And the important thing is that you have a box like this. I just also have these little bits coming off the sides. You don't need those. That's just me being a little bit sloppy. Really, if I want, go take all of this off. You don't need that. Okay. So what you do is, along the top, you put the second factor, okay? And along the side, you put the first factor, okay? It doesn't really matter which goes on the side, which goes on the top. You just pick something and go with it. In this case, they're identical, so it really doesn't matter. Then in each box, you look at what's above it and what's next to it, and you multiply them together. So a times a squared. Okay. Then you look at the next box. Whatever's above it and whatever's next to it at the front of the row, not just what's literally next to it. So at the front of the row, right? So a times h makes ah. And then for the next one, you look at what's topping that column, what's beginning that row, a times h or h times a, whichever. And then for the next box, whatever heads that column and begins that row, multiply those. H times h is h squared. So this does the same thing, and then you total up whatever's inside. So a squared plus 2ah plus h squared. This does the same thing, right? It looks slightly less like algebra, but it does the same thing. So this, if you want to use this method, if that seems easier for you, totally do that. If it keeps you from making a mistake, then you should do the way that seems easiest to you. Okay. Anyway, moving along. So next thing, we're going to work out what this big messy fraction is. This is something that's called the difference quotient. I don't recall off the top of my head if our textbook goes into any detail. Maybe it does. So if you just want to Google difference quotient, if you're just curious about what it is, you could look that up. Go on YouTube, difference quotient. It'll, you'll see what it is, and probably if there's someone making like a tutorial video on what to do, like in math class, what to do with it, they might also explain what it is. But you could look around if you would like, or again, ask me. So this part right here, this doesn't do anything for us. We can kind of ignore this. We don't need to worry about what its implications. That's a calculus thing. It's sort of redundant here, so let's just not worry about it. So what we're going to do is I'm going to rewrite this because it's actually kind of in my way, because I would want to put like equals and write more stuff here, but that's in my way. So let's do f of a plus h minus f of a all over h. And you know what? Actually, you know what? Ooh, hold on. My mistake. Let's not do that. Sorry. Let's summarize what we've done first. So we figured out what f of a plus h is. And we're using the same formula, x squared minus 16. So we've already figured out what this first piece of the numerator is. F of a plus h is this guy over here. Okay? So we've already got that. Okay? So now what I want to do is work out, well, what is the what is this whole numerator altogether? F of a plus h minus f of a. Now, f of a is just a plugged into the original function, so a squared minus 16, okay? So now, then what I'll do is I'll say, okay, I want f of a, wrong tool there. I want f of a plus h minus f of a, okay? So I'm going to copy that guy there, so a squared plus 2ah plus h squared minus 16, okay? And then minus f of a, which is a squared minus 16. Okay, now I'm doing something that's incorrect here, which I'll point out in a second. If you see what it is, awesome. So just maybe think for a second. What did I do wrong? What am I either missing or I left something out? So right over here, we're subtracting f of a. So we're subtracting the entire group here. Now what I wrote here is we're subtracting a squared, and then I wrote minus 16, which is, that's what the function does, right? But what that means is I'm only, according to this formula, subtracting just the next one. I'm not subtracting that one. It's already subtraction. I'm not subtracting the subtracted part, if that makes sense. Hopefully it does. I need to put parentheses here to group that together, because that minus 16 is actually supposed to be a plus 16, because we're subtracting a negative. It should end up being a plus. And if I don't put these parentheses here, then it won't be a plus and I'll get the wrong answer at the end. Okay. So now what I can do is I can distribute this minus sign. This minus sign goes onto both of those. So we'll have minus a squared plus 16. So this will be a squared plus 2ah plus h squared minus 16 minus a squared plus 16. And you might be noticing something. These 16s cancel, right? Minus 16 plus 16. And then also the a squares, the squared a's, the a squareds, I guess. These cancel because we have plus a squared and minus a squared. They cancel. And notice that everything we have left has an h in it. That's essential. When you're doing one of these on the homework, if you get to this point and you still have a term that doesn't have an h, you've made a mistake. That at this point, every term should have an h. Okay, that's the way it's supposed to work out. For reasons that I'm not sure if we can make clear at this time, because it would tie into what h is. So we can't really worry about that right now. Anyway, that's for the calculus class. So now we're going to form the whole fraction. All that stuff we just found divided by h. Okay. So f of a, wrong tool again. f of a plus h minus f of a, that numerator, which is what we just found actually, all over h. So 2ah plus h squared all over h. Now, what we're not quite done yet. What some people might do is they might go, oh, awesome, h is canceled. Perfect, we're done, right? Well, that doesn't quite work. And the reason is this h right here is not available for cancellation because there's another term involved. There's plus some other stuff. So that h that I've circled is not available to cancel. What we have to do, there's actually more than one way to write what we're doing, but conceptually there's one thing we can do. We need to notice that every term in the numerator has a copy of h and factor that copy out. So we have 2a, oops, we have 2a, and the h that was there gets removed, it gets divided out or factored out. And then plus, the second term has two copies of h, so one moves and one remains. And if you redistribute this out, you'll get 2ah plus h squared. I'm factoring out an h. Hopefully that's pretty clear. And then this h that's factored out, that one is available to cancel in the bottom. Later in the calculus class, when we covered this material that relates to this and we find out what a and h represent, this is really our goal at that point. The goal is to cancel the h at the bottom and get something that's not a fraction anymore. So 2a plus h is our answer, which might seem unsatisfying because it's not a number. It's just some letters. We shove some symbols around with some parentheses and some exponents and a fraction. And I don't know why we did this. We're just shoving some symbols around. Again, that's basically what we're doing, yes. But in the calculus class, this will gain some context where it's like, oh, okay, this is calculating something we need for calculus. And again, Zoom, office hours, be more than happy to explain it if you would like to know ahead of time what that is. Anyway, let's move along. So just some more examples. And I don't know if these are kind of out of order. Maybe these are out of order. I'm not sure. Anyway, so this one is talking about domain and range. And it mentions toolkit functions, but toolkit functions actually aren't part of these examples. I think the reason is these are based upon in Module 2, there are two sections in the textbook. There's 2.1 and 2.2, and I think that's the split, that this section is about 2.2. Again, this might actually be 2.1. These pages might be out of order according to the textbook. I didn't think to check that ahead of time. This is just the order that they were in the PDF. Anyway, so this says find the domain of each function, write your answers in interval notation. Okay, so the domain of each function, we were alluding to this earlier a little bit. The domain of a function is the set of numbers that are acceptable as inputs. And earlier I pointed out that I said something about multiplying numbers. A times h is h times a. It's the same thing when you multiply numbers. The order doesn't matter. And then I made a comment about, well, when it's numbers you're multiplying, there are examples in math where the order does matter because what you're multiplying isn't a number. So just to expand on that a little bit, for this class and in general in college level math classes, like like the 1,000, 2,000 level math classes, functions always take numbers as input. That's actually not necessary. The things that you plug into a function don't have to be numbers. They can be functions. They can be all kinds of stuff. You could have it where, oh, on a conceptual level, we're plugging shapes into a function. Like you have the function that counts the number of corners on a shape, that kind of thing, those are functions as well. So broadly speaking, the domain is the set of stuff that is allowed as an input. But for us, those will be numbers. So oftentimes when you're given a function, like in a homework problem or a test or something, you'll have like, oh, f of x, wrong tool again, f of x equals some function, I don't know, 2x times e to the 0.4x power, something messy like that. And you might be told, oh, this is in the interval from 0 to 5, right? X goes from 0 to 5. You can't plug in 6. It's not allowed. Sometimes you'll be given a domain and told this is the domain you're sticking to. That'll happen sometimes. When you're just given a formula, like in this case, the default assumption is that the domain is all real numbers which seem to work and not cause arithmetic problems. So domain, by default, our assumption is all real numbers that seem to work as inputs. And I shouldn't say that seem to, because then that's some plausible deniability. How about all real numbers that work as inputs? It's up to you to deal with the seems to part and try to, figure out what is it that seems to and what actually does and go through that. So basically, if I pick a number, like if I say g of 0, right? I want g, not f, sorry, g of 0. Right, that'll be 0 minus 4 over 0 minus 6. You reduce that, you get 2/3. So g of 0 is 2/3. That means that 0 is in the domain because when I plugged in 0, I got a result. Okay. If this were a live in-person lecture, I would then ask people, hey, what should we try plugging in next? And people will guess things. Let's try plugging in 2, because that one might be slightly interesting. So if I put in 2, g of 2, okay. Then on top, we'll have 2 squared minus 4. On bottom, we'll have 2 minus 6. So 0 over negative 4, that gives us 0. So we get a numerical answer, 0, right? So 2 is in the domain. And if this were in person, I would ask the class, hey, what number should we try that we think won't work? And probably someone will say, oh, let's try negative 2. And we would try that and go from there. At some point, someone will say, let's try 6, right? So if we plug in 6, I'm going to change colors here for a reason. If I do g of 6, okay, well, on top we'll have 6 squared minus 4. On bottom we'll have 6 minus 6. So 36 minus 4, so 32 over 0. And that's bad because you can't divide by 0, right? So 6 is not in the domain. The default is all real numbers that work as inputs. Well, 6 doesn't work. You get stuck because you can't divide by 0. So 0 is not in the domain. So one thing you could say is, oh, well, then the domain is all real numbers except 6, right? Like on an exam, because the exams are written, right? We'll talk more about that when we get closer to that. I'll make a Canvas announcement, of course. So all real numbers except for 6. So like on an exam, that'd be absolutely fine. That's the answer, right? Now, WebWork doesn't take that. You can't just type in, WebWork is not ChatGPT. You can't just type in a sentence, expect WebWork to understand what you're saying, right? It doesn't work that way. It's doing pattern matching, and you have to match the format. So the problems will probably say in WebWork, they'll say, oh, make sure to use interval notation. Okay, so we have to use that interval notation. What is that? So there's a couple ways to think about interval notation. So one way I like to think about it is I like to take this description about all real numbers except for 6, and then instead of talking about an interval immediately, I'd like to talk about a number line. So like if I wanted to indicate the domain using a number line, here's how I would do that. So I would mark the number 6 in the middle, perhaps. I might have like arrows on the end, so it's like a number line, right? I might mark 0 and 12 if I feel like doing that. So the domain is all real numbers except for 6. So I'm going to put an open circle at 6, which means we're not including it. And then I'll shade to the right and to the left, which this indicates, well, we're including everything to the right of 6, everything greater than 6, and then also everything to the left of 6, so less than 6. We're including everything else. This means everything except for 6, okay? If I wanted to use like a highlighter, right, I could highlight just those sections that we're talking about and skip over highlighting at 6 itself, right? It was a little redundant, but I could do it that way. When we go to the interval notation, I find this helpful because maybe it's plain that we have 2 separate chunks to talk about. So if I want to use interval notation, I'm going to have to list the 2 intervals separately and then put a union symbol between them, which we'll get to that in a second. So the way interval notation works, I'm assuming you've seen this before, but maybe you don't remember very well, or you see exactly where this is going, perhaps. Okay, the way interval notation works is you have a starting position and then a stopping position. You're saying, like, if you told, oh, I'm going to be there from 3 to 5 p.m., right? That'd be from 3 to 5. Like you're giving an interval of time, that kind of thing, right? Starting time, stopping time. So here, I'm going from, say, negative infinity all the way at the left end. I'm including all of that up to 6. So my starting thing is negative infinity. Not that that's a number, but it indicates we're starting all the way at the left of the number line. And then we're ending at 6. That gives me a stopping point, okay? Now, the next thing we have to do is we have to indicate whether or not these endpoints, the starting and stopping points, are included. Now, for the 6, we are not including the 6 because we're talking about everything except for 6. So we put a parenthesis that indicates we're not including it. If the problem were different or whatever, and we did want to include it, we use a square bracket. That means we are including, but we're not, right? We're not doing that in this case. And then for infinity or negative infinity, we're always not including because those aren't actually numbers. You can't do g of negative infinity. That doesn't work. It doesn't mean anything. You can't do arithmetic with infinity. There are ways to do that if you want to learn a lot more math, but not in this class. If you want to go get a math degree, knock yourself out, learn about transfinite numbers, stuff like that. Anyway, so then we're going to talk about the other side of this. Okay, so we're going to have another interval, starting point, stopping point. We're going to start at 6. Okay, and we're going to stop at, well, infinity is all the way at the end of the number line, so we're going to stop at infinity. And then I'll put parentheses around these because we're not including 6, because we're specifically not including 6. And then we're not including infinity because you always don't include infinity. It's not a number. And then between them, I'll put the union symbol. It kind of looks like the capital letter U. And when you're in WebWork, if you type the capital letter U, WebWork will interpret that as the union symbol. It's not literally the same symbol, but it'll work. Okay. So that's basically how you do that, how you find the domain by thinking about inputs working or not working. And then you can represent that with just a description in words. You can represent that with a number line, or you can represent that with intervals. And again, the interval version is what you're going to have to do in WebWork. On an exam, I'm not picky about it. We could also, well, let's not get bogged down. There's probably another way to write this, but this covers all the bases. Sometimes you can use inequalities rather than a number line or an interval. But let's not bother with this one. I think the later one's actually going to make more sense to do that. So let's move on to the next one. So here, we're going to find the domain for this one. And again, the default assumption is the domain is all real numbers that work and don't cause some sort of arithmetic problem. And sometimes the best way to get started is just guessing numbers. Let's say I want to do h of 0. So h of 0, that'll be the square root of 4 minus 0, which is 2. So that worked, right? How about 1? H of 1, that'll be the square root of 4 minus 3, right? 3 times 1 is 3. That's square root of 1, which is 1. Okay, cool. How about square root of, h of 2? I'm sort of guessing at numbers, not quite literally guessing. I have a little bit of a plan in mind. So this would be 4 minus 6, right? So square root of negative 2. Oh, that's bad, right? In this class, we can't have a square root of a negative number, right? As I probably talked about previously in the prior modules video, probably it came up, I'm guessing, it seems like it did. You can't have the square root of a negative number or any even root. 4th root of a negative number, 6th root of a negative number doesn't work. And there are complicated reasons for that. The short reason is that the types of problems you need to solve in business applications, like economics and finance, that area, complex numbers don't show up in those types of applications, at least not at the lower division undergraduate level. You might need complex numbers if you want to go get a PhD in economics, because it gets very mathy at the higher end of economics, right? So in some cases you need them. So for example, if you're an electrical engineer, you really super need complex numbers to calculate stuff. But for us, we really don't need it. So we'll just say add doesn't work. It's not that you can't do calculus with complex numbers. It's just very complicated, and we're not doing that. We're not doing algebra calculus with complex numbers. So next semester in the calculus class, we won't be dealing with complex numbers, so we don't need to understand them right now. That's basically the reason. But we do know that 2 is not in the domain. So I'm going to start, now that I notice this, I'm going to start building a number line representation of the domain. That might help me decide what it is. So I did 0, 1, and 2. So let's go 0, 1, 2. Now 0 and 1, these worked, but 2 did not work. Okay, so over here, some of this is my domain, some of this is not my domain, and there might be more that is part of my domain further, potentially. Like I could try more numbers, like I could plug in 3. If you plug in 3 to the function, it ends up not working. It also doesn't work. It turns out anything greater than 2 just does not work. Okay, so the next thing is okay, well, where, because I had a position of 6 that broke up my domain to pieces, right? So where is it between 1 and 2 that this is the last number that works? Where does that happen, right? And that you can do by guessing, but here's what really is the more straightforward way to do that. So the reason that we ran into a problem down here with this one is we had the square root of a negative, Okay, that's what caused the problem. So what I can do is take the radicand, the inside of the root, and set up an inequality saying, oh, this has to be at least 0, okay? Because when the radicand is negative, then that's not part of the domain. And I can solve this inequality and get an inequality description for the domain. So I'll add 3x to both sides and divide by 3. So 4/3 is greater than or equal to x, or in other words, if we want, x is less than or equal to 4/3. Okay, so that means up here on the number line, 4/3 or 1 1/3 right here. This is the last number that works. If you plug 4/3 in there, right? You plug in 4/3, you get the square root of 0, which is 0. Okay, so that means that including 4/3, that's part of our solution. And then everything to the left of that is also part of our solution. But to the right, these are not part of our, I shouldn't say solution, domain, sorry. They're not part of the domain. They're not solutions to this inequality, and they're not part of the domain of the function, okay? So when you have a square root, set the inside, set up an inequality greater than or equal to 0, and solve that inequality, and that will get you where the domain is, okay? Now, as an interval, I can either think about looking at the number line, because I did draw it, I can think about those terms. I can also just look at this and say, well, I want everything less than or equal to 4/3. So I'm going to start at negative infinity and go cover everything up to 4/3, including 4/3. That's another way to do it. So that would be negative infinity up to 4/3. And I'm using a closed bracket because this says we're including 4/3, right? X is less than or equal to 4/3. That's also why up here I put a solid dot at 4/3 because that indicates we are including it. So to summarize, if you have less than or greater than, that's equivalent in a number line to being like an open circle on the number line, and that's also equivalent to using either an open or closed parenthesis, as the case may be, whether you're at the left or the right end of the interval. If you have less than or equal to, or you have greater than or equal to, well, that's equivalent to doing a filled-in dot on the number line, which is then equivalent to using brackets on the interval. So the inequality symbols here correspond to the line graph symbols here, which correspond to the interval notation there. So you got a little chart that tells you what's related. So not include. So let's say this one is not include. Let's call it that. Let's call it what it is. Exclude. It's exclusive. Okay, and this one is inclusive. Okay. All right. So hopefully that kind of made sense. This one is kind of easier because you just start picking numbers and you notice pretty quickly that they all work. Like if I do f of, I don't know, 7, something like that. Maybe 7's a bad number to pick. So that's 2 times 7 cubed minus 7, right? That's going to be something. Let me get my calculator. I want to say 7 cubed is 243 from memory, but I'm not confident in that. 343, yeah. So 343 times 2, and then minus 7. So 679. I get a number, right? And no matter what you pick, you get some number. And so, like with this one, pretty quickly by guessing, we got something that didn't work pretty quickly, and that made us realize, oh, we're going to have to set up an inequality and figure out like where is that breaking point. This one, everything works, and so how do you when you're guessing numbers and every one of them's checking out, how many times do you check before you sort of give up and go, well, I guess the domain is all real numbers. They all seem to work. I've tried like 10 things. How do I know when I conclude the domain is all real numbers? So part of the problem with that is the technical answer is you can't. Guessing and checking is not conclusive evidence, right? So, at some point you become confident enough, like I'm tired of checking stuff. I'm pretty sure the domain's all real numbers. I'm just going to put that. I'm just going to go with it because I'm pretty sure because I've tried enough things. Another way is to think about, if you plug in a number, think about how PEMDAS follows. When I did this, what happened, right? I picked 7 to plug in, so I have to cube it, right? When you cube something, when you're cubing the input, is it possible for that to go wrong to where you get stuck trying to cube something? Up here, it's the square root that introduced the issue. Sometimes you can't square root something. Sometimes, right? When you're cubing, you can always just cube anything. Because remember, cubing is about multiplying. This cube just tells me, take that thing you plugged in, take 3 of them and multiply them all together. You can always do that. You can always just multiply numbers together. Square roots, not always. Division, not always, right? You can't divide by 0. Did we see that earlier? I think we might have. So yeah. So think about what happens when you're following PEMDAS. What happens? Is there any potential it's going to go wrong and we get stuck? And for cubing, there just isn't. The next thing that happens is times 2, right? 343 times 2, right? That's what I did in the calculator. That's always going to go right. You're never going to get stuck. Like, oh, we can't times 2. Like, yes, you always can. Then subtract 1. You always can. So just by looking at this and going, oh, that's a polynomial. It's a cubic polynomial. There's no roots. There's no division. It's just exponents and numbers and multiplying and subtracting. There's no division. There's no square root. So nothing can go wrong, right? So the domain's all real numbers, okay? So sometimes you can conclude that just by recognizing, oh, this is a polynomial. Wrong tool there. This is a polynomial. I'm not going to get stuck plugging in numbers. It's always going to work. So that you just kind of have to learn through experience. Anyway, so this one, we're almost done here. This says write the domain and range of each function, write your answers in interval notation. Okay, cool. So this involves a little bit of guesswork, and I apologize like a little bit for the blurriness of the image. These could have been done better, but they're good enough. And we're zoomed way in. When you're zoomed out, they look fine. But I'm zooming way in. And when they're printed on paper, they look fine, actually. So the domain is all of the x-coordinates that the graph seems to be using. Now, we can tell just by looking that there's no graph over here to the left of -4, right? Now, do we know for sure that there isn't actually like some more graph over here? Well, no, we don't know that, I guess, but we basically have to assume that the graph presented shows us the most important information. Also, do we know that this doesn't curve like that and go back down again? Well, I guess we don't know that, but we have to assume this is showing us all the important information. Now, this one you might think is a little bit hard to read because does this keep going up higher and higher and higher? Or does this one seem to flatten out? And it's not so obvious if it flattens out or not. So sometimes it's real clear. Sometimes not so much. I think with this one, it's not clear. So I'm just going to assume that it keeps the trajectory that it's doing, which it seems to be tilted up a little bit. So that means it's slowly going to keep going up is my assumption. Okay, I have to assume that I'm being shown the important information, that nothing weird is happening outside of the frame of the graph. I have to assume this is the important stuff. Okay? And because this is an arrow, it continues. This is a closed dot, it does not continue. I'm not talking about, oh, what does this one do? I know it stops there. Oops. It stops there because that's what the graph shows. So I know that from left to right horizontally, we're starting at -4, and then we're just going horizontally all the way to the right. So my domain will be from -4 up to infinity. Again, the arrow suggests to me that it keeps going. I have no indication that it stops. On the left, though, I have an indication of where it starts. So domain, we're going to start that at -4. Okay. And then the range, like I said, the range is a little bit harder, I think, sometimes, often, I suppose. So we're starting here at -2. That's -2 on the low. Remember, the range is the vertical space that is covered by the graph. So we're starting at -2, and you might think, well, maybe there's actually an asymptote at 4, and then this graph just gets next to that asymptote but never actually crosses it. And so the range stops at 4. Well, okay, yeah, but that's you adding extra information. You're adding context that isn't directly shown. So if the graph showed, oh, there's a dashed line right here, then I go, okay, that's an asymptote. They're telling me it's an asymptote. But absent that, I see no reason to believe it doesn't continue growing vertically as the graph continues to the right. So I'm going to say that the range is -2 to infinity, just based on what the graph appears to be showing. Okay. Is there another one here? No, there's one more here. Okay. So next one. Now, maybe this one's a little bit harder, perhaps. So remember, with domain, I'm looking at the x-coordinate. With range, I'm looking at the y-coordinate. Okay, so think about the x-coordinate first. I see that we've got a starting point here and a stopping point here. So horizontally, we're starting here at -3, and there's a closed dot, meaning -3 is included. That's part of the domain. You plug in -3, you'll get -5 as an output. Okay. Now horizontally, we stop here at 2, but there's an open circle, which means that the graph doesn't actually have a point there at x equals 2, like the order pair 2, 0. There's actually a gap there. There's no point there. So 2 is not in the domain. So for this one, I'm going to say the domain is -3 to 2, including the -3, so bracket, not including the 2, so parenthesis. Okay. And then vertically, this might seem a little weird, but vertically, we're down here at -5 is our starting point, right? And then there's a closed dot saying that's what we're starting, right? And you might be tempted maybe to stop here vertically, but no, there's more verticality there. So vertically, we stop here at 4. Okay, that's the highest point on the graph, the highest y-coordinate. And it might not be totally obvious because here at this position, there's no dot, there's no circle, there's neither. There's just, the graph is just curved there. So at a curved point on the graph, that's sort of the default of saying there is a point there. When we have an endpoint that is a soft endpoint missing, like there's a gap at the end, we put a circle. And when we have a filled in dot at an endpoint, that means that we have part of the graph there, right? If we don't have anything drawn, the default assumption is that would be a point. It's just, if you start drawing a point at every point, you get a thicker line, and then the points aren't even visible. So basically, generally, we don't put those points at positions that don't need them. The endpoints need them. You got to put something there. You put an open circle or a filled in dot, versus the middle part of the graph, you just put part of the curved graph there. So long story short, we're ending vertically. We end at 4. So the range here is -5 to +4, inclusive, because it would be a filled in dot. And I think that's everything. Did I miss anything? No. Okay. Anyway, that's that. Hopefully that made sense. Again, as I've said, and I'm sure I'll say again in the future, if you need assistance, email me. We'll get on a Zoom call. I'll help you figure it out. But yeah, that's module 2.